so there's no interrupting. So let's go to the minimum model. Over the interval, well, over the break, so there were interesting questions about the training objective. So that's also what we're going to talk about in this part of the talk. But before that, I will talk about the minimum model, which we haven't talked about. So for the minimum model, the essential criterion is that we want to have valid likelihood, so conditional likelihood, and that is not something directly available from some of the early solutions that I will discuss very quickly. So again, we don't have to have this brute force approach of using neural network to learn about everything. So sometimes with deep learning, you just use putting neural networks in all those different parts and then learn it. However, if we have known distribution, like in this case for stochastic volatility model, by itself is differentiable, and also we can evaluate the density exactly because there's functional form. Then we can directly basically parameterize this in this way. But of course, there are instances where this likelihood is not easy for us to directly infer. We don't have that parametric form. For example, think about the autonomous driving example. We have those images and we have those states, and states, as I said, can be even the driver intention. How can we measure that? Well, for some of the early work, for example, for this seminal work, so differential particle filter, so at RS 2018, it basically takes the observation and state as an input, and then the neural network just outputs a scalar. That scalar is used as a likelihood. So they just ensure that this scalar is positive or between 0 and 1. So let's say sigma is there, and then just to ensure that. So it works well in their in that application because they are doing individual training and also some type of end-to-end learning with a ground truth there. But later, once we start to conduct more exploration on unsupervised learning, there are issues there. Because I will later mention that, well, maximum likelihood, as we discussed a lot, so that is a common principle we use to train, optimize those parameters. If we have those state observation as an input and have a, let's say, bounded function output a scalar between 0 and 1, it's very easy for neural network to cheat. The reason I mean by cheating here is that to maximize the likelihood, the neural network can just output 1 all the time. And that in that way, you optimize, you maximize the likelihood. And the reason this can happen is that this way of constructing the conditional likelihood does not give you valid probability density, right? So just get any input there and you output a scalar, it's not normalized. So that is an issue. Well, initially to address this, we simply encode the observation and state into a feature space with the same dimensionality. And then we can use, for example, use a cosine distance or another non-parametric, well, so basically with a function that we do not need to learn any parameter just to compare the distance. So in that way, we kind of like force the neural networks learn something about the observation and state so that they can be mapped to each other. And also we want to ensure this encoding ET, if we have put a decoder on top of it, can reconstruct this OT. So again, to avoid the networks to cheat, so that it just output some constant that is always equal to this one, and that means nothing. So we want to make sure that those two features are really some meaningful representation of the state and also observation. So this is just one way to address some of the issues that we discussed in the earlier type of likelihood in differential particle filter. However, this is not a really perfect solution for this, I would say, because still this type of cosine distance-based density is not a valid density. So how can we do that? So what's your thought? How can we develop some likelihood of using neural network and still lead to, let's say, valid density? Well, we talk about something similar in the first half, normalizing flow, right? So normalizing flow can be used to convert density or generate a valid probability density. However, normalizing flow cannot be directly used here. If we think about the example I talked about in the beginning, to generate either samples from the proposal distribution or from the dynamic model, the neural network output and also input have the same dimension because it's based on or conditional upon your state as a previous time step, so st minus 1I. So that has, let's say, capital D dimension, so dimension capital D, and the output the state as the next time step, so the same dimension. And then the way we construct that real MVP really means that we have the same dimension between the input and output, as we show in that early example about the normalizing flow. So we cannot directly using normalizing flow to construct a minimum model in that way, because here we want to output a scalar. If we, and then the scalar does not have the same dimension as observation. But this can be quickly work around, because again, we can use normalizing flow, but instead of outputting the likelihood directly, we can output just a Gaussian sample zeta, Z here, having the same dimension with this observation O. And then the reason that we want, it's useful to do this is that, well, because this Z is a Gaussian sample, so it's very easy to evaluate the density. And also we have an invertible transformation. Then by using change of variable, we can basically very easily to compute this conditional likelihood, right? So P of OT given STI and theta. And this STI, well, conditioning part, we can use exactly the same trick in the proposal density, in constructing the proposal density, putting this as just a parameter for that C and T functions. So that is just means that this is well, we can condition on the states to construct the density of OT. And so here are a few choices that we can use. Again, this is definitely just some of the let's say, initial exploration on this. But right now we are pretty happy with this conditional normalizing flow. Of course, there should be different approaches there. So to summarize, so likelihood is directly available, then we can just directly evaluate that likelihood. Also, there are early choices of compare features of observation and states, but you don't have valid probability density. And then lastly, we can have valid densities through conditional normalizing flow as option 4. Okay, any question about this before we move on? No? Okay, fairly straightforward. I think that, this part, so just to highlight that we don't directly output the likelihood, but then just use a change of variable to evaluate that. Yes.
Why did we have to increase the dimension? Because you said like with the scalar doesn't work. Why does it work with the?
Okay, so this goes back to what we discussed here, right? Or even what probably goes here. So here for normalizing flow, you really need to have both the input and output have the same dimension.
See, here.
Because otherwise they cannot be invertible. No more questions, then let's go back to the resampling part. So well, as we discussed in the beginning, the inverse CDF is a step function, which really causes all sorts of issues. So it's non-differentiable, and also small change of weights will really just change a slight difference among those boundary. And if you think about, let's say UI have been sampled, so the update of your network parameter will cause slight change among those boundary, but this will not cause continuous change of your resampling output. So that kind of cause issue among other issue there. So one option to bypass this, or kind of, let's say, partially bypass this, is through soft resampling. And that is quite similar to, there's some relationship with what Victor talked about. So in terms of resampling directly from the target distribution, we can resample from another distribution. So in this case, we can resample between a linear interpretation between the actual target state and also the uniform distribution over here. So this is still valid, normalized importance weight we denote by W tilde star. So we really overuse all of those symbols there. And then, as Victor mentioned, so if you do not resample according to the right distribution or the target using the target weights, you need to correct that bias by sampling from, by this time, because this is your target distribution. So if lambda is equal to 1, where you directly sample from your target distribution, then you don't need to correct the bias. But then now, if lambda is, let's say, less than 1, you need to correct it accordingly. So in this way, you will have the weights after resampling as a function of the initial normalized importance weight. So then we can basically approximate the gradient. So with some non-zero gradient, which is a function of your weights. So that's just one way to bypass the issue. And so as I just said, so it's similar to the resampling in auxiliary particle filter. So you resample from another distribution with some purpose. In this case, to approximate some non-zero, or pass some non-zero gradients there. So we resample to get this W tilde and I. So instead of, so basically to get those samples, so STI, but then with new weights, and then we need to correct the weights by the amount shown by this W tilde hat there. So the problem there is still not fully differentiable. You still rely on inverse CDF, but just with a different CDF function. And then, so small change in weight still will cause discrete change in resampling output. And also the resampling output is not uniformly distributed, because with resampling, we would like the, or at least there are some benefits of having uniformly distributed samples so that we, to reduce the variance. But in this case, you don't have the uniformly weighted sample because you need to correct the bias. And so that is why in this case, the variance increases.
You are differentiable with respect to what?
With respect to the important weights, yeah.
So when you do the resampling, how you make it differentiable?
Well, it's not, yeah, indeed, as you correctly mentioned, so yeah, it's not really differentiable. It's just that you pass through some gradient, so some information of your original weights. And now,
just in the weighting.
yeah, just in the weighting to pass the gradient information there. And that is why this motivates this piece of work. So using optimal transport to do resampling, completely get rid of this inverse CDF. So to do this. So inverse CDF algorithm is not used in optimal transport based resampling. And for optimal transport, Sahani mentioned that yesterday. So basically it is a way to transport a source distribution mu to a target distribution mu, assuming that you know the point-to-point cost to do this transportation. Then what is the optimum arrangement to transport all of the masses or samples from this source distribution to the target? This is basically an optimization problem. And the idea is that you want to find a way to transport the masses to minimize the overall cost there. And in particle resampling, we basically want to find a way so that we can basically target the impurity distribution. So for example, if your source distribution is your resample particles with equal weights, and you want to find such arrangement or such resampling, let's say, scheme, so that that distance between your source distribution, so your resamples particles with respect to your original samples, STI with original normalized important weights to be minimal. Let's set it clear. And then I will talk about more, let's say, purely about optimal transport. What does that mean? So optimal transport has been an old problem. So it started from, let's say, more than a decade ago. So Monge look at this in terms of finding a function from the source domain to the target domain. So basically that T such that the distance, the expectation of the distance of X and also, well, so the distance of X and also the transformation or transportation outcome is minimized. So basically satisfy the fact that you basically after this transformation, your source distribution will be transferred to your target distribution and this MT is minimized. So a one-dimensional example, if our source distribution are those blue points, so those are just masses equally weighted, and then those red ones are the pits we need to transport those samples to. So there are different arrangements. So this capital T can be different ways to transport those samples. So you can transport these samples to here or to here, right? So those are just different functions we can use. So if the point-to-point cost to transfer one point to, let's say, this point or this point is equal to the Euclidean distance between those points, then the optimal way to transport samples, well, you can guess, is perhaps just do this orderly. So for this one, because it's a blue point on the left-hand side, you just transport the sample to the red pit. So also on the leftmost point, and then transport this one to the second one, and transport this one to that one. And you can actually show that this is always the case. So basically order them in one-dimensional cases, and then just put those, let's say, masses according to that order. And this will be the arrangement or this Monge map that minimize the overall cost. So that is just in one-dimensional space, it's very simple. And also in our case, it's actually very useful that also we have some also, well, it's not exactly one-dimensional. So, but just I want to use this toy example to show what is a different key function here. But the problem for Monge formulation of the optimal transport is that it's yield-opposed because sometimes there's no such a mapping satisfying that you can transport all your source distribution to your target distribution through the Monge map. The reason for this is that, well, in this case, we have just seen, well, there's a Monge map to transport the blue points to the red pits. But how about this case? You have your source distribution here, so have a, let's say, mass larger than the others, you have, let's say, 3 points there. For the Monge map, because it's a valid function, so there's a one-to-one correspondence. Well, you know that, well, perhaps for those two, we should transport them here and here. How about this one? Because T is a function, so you, with the same input, you can just go to one of the places. So this one, this is undefined, how this should work, right? So how should we bypass this? Well, after, let's say, a few decades, then Kantorovich came up with a Kantorovich formulation. So instead of directly looking at the mapping, so finding a mapping function, there can be a joint distribution. So there will be a joint distribution pi. And the condition is that the margin of the joint distribution will be the source distribution and also the target distribution, respectively. And then an illustration of this is that, okay, assume those are our, let's say, marginal distribution density here, as we see. So those are discrete. And then there's one of the valid joint distribution will look like this, or joint probability. So there can be, let's say, more masses here and more masses here, but those can be, let's say, split between those two different blue points. And then if you check the marginals, they will correspond to the right, let's say, marginal of the source and also target. It's just one way to do that, but also you can have a diagonal like that. And then the point of finding the optimal transport map is to find the joint distribution that minimize this overall cost. Because this basically define what is the expected cost when you transfer all of the masses from one distribution to the other. So C of xy is your point-to-point distance. So optimal transport is always about if we know what is the cost to transport from any point to another point. If we know about this, what is the best arrangement overall? And this basically, this objective tells you what is the best arrangement overall. Do you think this is a hard problem or easy problem? Well, the fact that in the last 15 years, there were 2 fields methods working on this, so basically shows that this is a pretty hard problem. But this is also a very important problem, as you can see. And we'll see how this can be made more computationally, let's say, efficient. Another, let's say, illustration of what this is doing is that, well, there will be one joint distribution or joint probability in this case. So for example, this is a joint probability, and then we can see that this essentially define a transport map, because this one basically shows that for this point mass, of this point with point mass of 0.5 probability, half of them should be distributed here, half of them should be distributed here, because this just means that 0.25 should go here, 0.25 should go here, right? So that is why this joint probability actually define how the distribution should be mapped. And also this kind of resolve the issue with a Monty map. You can only map one point to a specific point. So here you can actually go to different point. Is that clear? And then basically this transport map gives an approximation to the Monty map. And then this gives the so-called Barry center projection map. So now, once we have obtained this joint distribution, then based on the, let's say, on the initial sample we have, so before resampling, we basically can have a weighted average to get the new samples, to get the new samples after resampling. So in this case, for example, basically, if those Y1, well, if let's say Y1 and Y2, and also those points are our, let's say, samples before resampling, after we get the optimal transport map, and we can basically have a combination of those old samples and get the where the new samples should be. Now, perhaps you have seen one problem of this one. Well, there are several problems of this approach, although it makes the whole process differentiable. I haven't touched upon why this is differentiable. But the problem here is that in the regular resampling approach, all of the resampled points will be the same particles. It's just some particles survive, some particles die. But in this case, you will actually generate new particle location. By the way, they construct so how this one, this resampling method is proposed, and this may cause some issue. But this is how the method is proposed. We first learn about the joint distribution that minimize the distance between, let's say, any between unweighted, between equally weighted particles and also the correctly importance weighted samples, and you use that joint map to learn about where the resample particles should be. So this basically summarize the process, as I just said. So find the transport map from a source distribution here. So STI are just a sample, so the NP particles before resample, after resampling, so that so they have the same equal weights, and then to the target distribution, so the correctly sampled particles STI and W tilde TI, and then we use that to find the joint distribution to minimize the distance, and then you use that to construct the new where the new samples should really be. And then now I'm going to talk about one issue of finding this pi, because finding this pi is so difficult, as I said, so that's why it's active research area. And then for the resample output is that you have the same equal weights, but then the resample particle will be those linear combination interpolation between samples based on your optimal transport map. The problem of finding that joint distribution optimal transport map is that it's computationally expensive and also non-differentiable because it's, well, it can involve different optimization solvers, and also it's really computationally intensive. So there's one seminar paper on computational optimal transport, and that's really one reason behind the current, let's say, interest in machine learning community on optimal transport is that Kuto show basically that by adding some entropy regularization term into the as part of the optimization objective, we can basically convert the, let's say, optimization problem to some iterative algebraic operation. So make it more efficient and also converge fast and also make the whole process differentiable. And so for this resampling method, you just directly use that Synchron algorithm proposed in 20 to solve the, let's say, optimal transport map efficiently. And then once that, the only thing you need to update is your optimal transport map. So from this pi, initially as a optimal transport pi to this optimal transport pi zeta. So this zeta is essentially as a entropy regularization. You just need to add something very small, the entropy noise, but don't be too small because otherwise the algorithm may not converge. But then this basically allows you to have an iterative approach to find this pi, and then you can use that to generate this. To summarize, there's a soft resampling approach to kind of pass a gradient, but it's not fully differentiable. And also it will lead to non-uniform weights, but higher variance. It's easy to implement and also low, also has no computational overhead. So it has been quite, let's say, popular in this field. And then there's a more justified, or let's say, approach to make it more, so the first fully differentiable approach to have this entropy regularized optimal transport resampling. So there's no multinomial resampling at all, or other type of inverse CDF based resampling. And you resample based on an optimal transport map that you can learn from the Synchron algorithm. And then the one of the drawbacks is that the resample particles are not from ancestors. That may cause some issue in some application, and then better performance with the cost of more computational overhead. So that is a quick summary. And I think this is definitely an area that needs more, let's say, research, and also there's already existing other work on this. Yes.
So maybe I should have asked this a while back, but when we talk about differentiable resampling, we are thinking about the derivative of the new particle with respect to the old particles, right?
Yep.
So how do you do this in the soft resampling case? How does it work? Because this is just resampling with some different weights.
How should I approach this? Well, it's really a way to bypass, to pass a gradient. It's not fully resample, so it's not about, let's say, compute the, let's say, directly pass the gradients. I don't know if that really answer your question, because later I will talk about what is the training objective. So training objective is basically the function of those states and also those weights. And then as long as those importance weights, they basically appear, so the function of those parameters appear in the training objective. So that is how is a gradient, and that is how you optimize it. Another question?
The leading question: Are there other approaches to differentiable resampling?
Yes, I don't have an exhaustive approach there, but we were discussing the other approach we haven't included here. So just to talk about really here is to talk about what are the issues here, and then some of the popular approach, but this is not exhaustive at all.
You know, because I mean, so I work on this stuff as well. So it's kind of like these two approaches are kind of like, you know, the earliest ever approach really, other than basically not doing any resampling, and maybe the most modern approach in terms of like developedness, not necessarily in terms of publication date.
Well, so
There are, because there's other approaches that introduce bias in the
Yeah.
gradient. So the entropy regularized optimal transport one is unbiased in terms of the gradient of the weights, which is the thing that we really care about because of the differentiable resampling, whereas the soft resampling one is biased. And there are kind of ones in between that are unbiased. There's like stock gradient methods, which are
yeah. So that is one thing that we are aware of, we haven't included there. So I think it's just that there are so many different design choices. It will be useful, I will mention in the end, that we have some common data set to evaluate this. So this is still like more, let's say, machine learning approach. It's difficult to evaluate. Well, of course, we can evaluate through, let's say, bias and variance. This is not something that right now for us, we have been really working on the other parts of the components and then directly using some of the effective approach that I'll say.
I mean, at least my understanding is basically the questions being asked here is how do we sample a categorical distribution in a differentiable way, which is a very broad question to ask.
Yeah. There's no more questions, so I will go to the final part, training objectives. Well, this should be something that we can discuss from the beginning. So that different strategies between DPF, so individual training, so train each component of DPF, so differential particle filter individually, and that was discussed in the initial paper, or one of the initial seminar paper on differential particle filter. So basically, if we know the ground truth, that is also assumption in that paper, how we can predict the next state better, just in terms of how to maximize the density of them directly from the dynamic model, and also individual training of the minimum model. So how to maximize the density of OT given the right state, and also minimize the density of OT given a wrong state. And that is what they do. But also you can do this in terms of end-to-end training scheme by jointly training all the model components by minimizing all quantity derived from filtering. And that actually does not have to be about filtering. It's more about, let's say, because this actually should also be about smoothing. This has not been something that has been explored before as far as we are aware of. And then in terms of individual training, the individual training of that dynamic model, learn how to predict the next state. Well, we can basically maximize the true state of likelihood. So like this. So if you know the state, whatever way you learn about those hidden variables from your experiment and timing, as we discussed in that toy real world example, when you can maximize this. And from here, so from this training objective, so you will only maximize the objective related to the parameter with respect to the parameter in the dynamic model. And then there's an individual training of measurement model, so learn to maximize the likelihood of OT given ST star, and minimize the likelihood of OT1 given a state not in the same time step, just assuming that your state always evolve. So that is how one of the training objective was derived. So you may not feel this makes sense, but this is really like one thing have been used in the beginning. Yes.
So in the first equation, summation is over I, but I don't see an I on the right-hand side.
Okay, so
Over particles or over time?
Over both.
yeah, so it shouldn't be there. So
But S star is the ground truth, right?
S star is a ground truth, so it's the particle.
Particle aspect in that.
Yeah, jet true. So thank you. Yeah, this is a mistake there.
Ground truth, you mean that it's like a supervised kind of scenario?
Yeah, supervised setting.
You know the location of object that you're tracking or exactly and.
Absolutely, absolutely. And with the end-to-end learning, then that requires you to use the particles. Although here, basically, the ST is your particle estimate of the state, and ST star is a ground truth. So again, so in a supervised learning setting. And again, and also another way is that if we assume the particles form a Gaussian mixture with weights Wi, and then we can take the negative log likelihood of the true state as a training objective here. But for all of those, the assumptions, so as you rightly mentioned, is that you need to have access to the ground truth, and that can be restricted. And I think in the spring break, we talk about some of the real world data sets that we feel interested in. For example, if we want to track the state of some, let's say, phones on a Google scale, because Google right now has a challenge, let's say, predict states based on those GISS data. You can have, let's say, millions or billions of phones, only a very small percentage. You may do some expensive experiments to know the actual state. So this is actually restrictive of those objectives.
And in the mean square error, the ST is the output of the particle filter,
Yes,
which is a function of the parameters theta.
yes.
But I guess it's like the mean of the particles or something like that.
Yeah. So, yeah, this is not consistent. So I should, basically it's the ST hot, SRT. For both of those two options there. So it requires true state at each time step, and can we, let's say, reduce some of the issue there. So the first thing that we can think about is to use a pseudo likelihood. Well, one thing I can mention is that this is they call end-to-end learning. So in this paper 10 and also using 17 is that, well, because you are using the particle filtering means, so you basically so this is a function of the parameters of the neural networks. And they directly maximize this filtering objective, so to make sure that all of those components, including the dynamic model and the measurement model, those parameters are selected, optimized in a way to maximize those or minimize those losses. And then there's also pseudo likelihood for unsupervised learning or semi-supervised learning, depending on how you incorporate the information you have for ground truth. So essentially, we want to optimize the data likelihood, but then as in that online EM, you don't want the dimension always increase and your computation costs increase. You can split the data into blocks and then maximize over those sum of those log of the pseudo likelihood. So pseudo likelihood because it's a likelihood of blocks of observation instead of the whole observation. So instead of going into detail, because well, I think we in online EM we discussed it. Yes.
Perhaps I missed this, but so when evaluating the likelihood of a block, how does one initialize the block? Because in classical particle filtering, you only have the initial, like a prior on the start state at the very start. And when you're blocking the series up, how do you initialize each block? Or is that something that's just coming?
You just wait until you have L observations for that initial block. So you have that observation.
And then you use those as the prior for the next block.
Oh, so I think there are differences. So we first need to initialize the parameters because this is iterative approach. So assuming you have some, let's say, even that estimate of the parameters, you can use that to perform filtering, and you can use that to evaluate the, let's say, approximation to the pseudo likelihood. And then you do this iteratively. And once you have finished this, so you have a set of parameters that you are happy with, and you use that to generate to perform filtering, and you use that as a, let's say, you're not using that as a prior because those are separate. As you can see, those are the sum of different log pseudo likelihood. You definitely need to assume that there's a stationary distribution, but that can be, let's say, based on some other.
Yes, so if you assume stationarity, this is fine.
Okay. Other way to do this, so is to directly use a marginal likelihood-based loss. So basically, we can factorize the log likelihood, data likelihood, like this, so as a sum of the log likelihood ratio, right? And then this log likelihood ratio actually can be basically approximated by the sum of, not sum, the product of those, no, sum of those, let's say, unnormalized importance weight. I'm not going into the detail, but this actually can be approximated. And the interesting part is that those are things that you get for free. And then you get an approximation to the log likelihood. And then there's some interesting connection that John-Ju actually derived and also basically discussed also by Sahani yesterday. So I'm not going to into the details here. So basically, by minimizing these SMC-based training objectives shown here, we are essentially minimizing or maximizing an elbow that we can basically optimize the data likelihood by raising the lower bound and also minimize the distance between the posterior that we are targeting and also the proposal distribution that we are using. So essentially, this means that we optimize both the model parameter theta and also the proposal parameter phi, in a sense that it helps the filtering. So the question here, so what is the likelihood elbow gap? So basically some standard rational inference derivation. So we can skip here, but the solution or the conclusion here is that we can optimize the elbow is simultaneously maximize the observation likelihood and also minimize the KL divergence between the approximate posterior and also the true posterior here. And this basically there are also different variants of those VAE-based elbows. So you can basically have different samples there, and different samples from your proposal distribution and how that leads to variants of the training objective that may have some benefits in your training. There are quite some choices there. And then in terms of comparison, yeah, as we just discussed, so it's just a way to optimize the observation likelihood and also drive the proposal to the posterior. And then the different choices have the implication on the variance of the training objective you obtain. And for us, we just use the simple approach and to see how it works. And the SMC elbow itself is adjacent lower bound to the true variational elbow. We have shown the empirical how empirically this is effective, although we haven't really rigorously shown how those different approach or different training objectives are, let's say, in terms of their theoretical. And then, as we discussed in the beginning, so of this session, so we have those problems that you have a large amount of time step. You know the observation, of course, observation are always available to you, but only a small set you have the ground truth. Then how we can perform the semi-supervised learning or the naive way just to have optimize the linear combination of the MSE across a restricted data set and also the elbow across a larger data set. Okay, I think it's time to look at some numerical experiments. So there are a number of experiments that we have been doing. So there are those linear Gaussian experiments, so one-dimensional space and also higher dimensional space. So in this way, we can basically know what is let's say, the optimal filtering results and then perform combination. But also there are some numerical experiments we have explored. So for example, there's a disk tracking experiment. So the idea here is that observation as particular time step O is that an image that shows a location of disk at time step T. So here there's a well, you can see So here, this is a ground truth at that time step, but there are those distractors. So states is a location of red disk, but then the noise comes from those distractors. So those other disks of other colors. And then challenge is high dimensional, so because those are images, and also unstructured observations. And then there are moving distractors, and the target also may disappear from the observation because they are occluded. Then the dynamic model look like this. So for there will be some action that have basically there's some additive noise there, and then the state of the red disk can be generated through this way. So the true state plus some noisy action plus some Gaussian noise with a potentially or very likely different Gaussian noise. And then the question is that how to model the relationship between observation and states. So what we do here, so that's just a design choice. So you definitely are free to make other design choices. So you can encode OT with neural networks to some feature space, E theta, estimate the conditional likelihood using the approach that we discussed. And also there are different approaches, as you will see later. So we'll compare it with a number of existing methods and see how it performs. And then proposal, so we utilize the encoded feature ET, and then we can, for example, in that normalizing flow-based proposal, we can use that ET as a conditioning part, the input to that state and also variable. And then for the loss function, so we are using a combination of the losses. For example, in this setting, so in the training data set, there are ground truth available. It's a numerical setting, so you can use the RMSE between the filtering results and the ground truth as part of the training objective. But also there's an autoencoder loss. So basically for this feature, we want to show that this feature learns something meaningful. So if we stack another decoder out of it, on top of it, it should be able to reconstruct this OT by minimizing this difference between the decoding output and the real observation. So for the dislocalization experiment, so we evaluate the methods with a number of algorithms. So the NFDPF, so it's a normalizing flow-based differential particle filter. So that one, well, we call it NFDPF, but also there are a few other approaches, the early approach, so PFNet, and also the autoencoder based SMC method, and also this particle filter RNN network. And in terms of training, we have 500 trajectories as our training data, and each trajectory have 50 time steps and then 50-50 for validation and testing. And then 100 particles used in training and testing just to make it more efficient. So here is how it looks like. So for example, in the initial time step before we perform any filtering, and as you see how you initialize particle filter, you put those circles or those particles just across the area. And then the true state is over there, and then you have those, let's say, distractor there. And then this green star is just your particle estimate. And because all the particles are just uniform distributed across the field, so the particle estimate is really quite far away from the true state with this blue or purple triangle here. And then once you perform filtering, and we can see that those particles start to quickly go to the approach to the real state, showing that the tracking is successful. Well, one thing I want to highlight is there's offline training already happening. So basically, this shows that okay, after training, we can basically get the particle filter, so learning those components using the neural networks and learning some at least sensible model and measurement model that can perform tracking with all of the distractors. And then in terms of the performance, so in the training time, we can see that well, as the training epochs go, this normalizing flow differential particle filter really converge to the lower value more quickly compared to some of the other methods. And also the validation RMSE also is the lowest after convergence. And then in the test time, with those 10, 50 test trajectory, we can also evaluate the filtering performance. Also, in the different time steps, it has the lowest, at least the mean filtering errors there. Any question about this setup? It's just a one easy setup we choose. And the reason that we have this intermediate numerical setup is that, linear Gaussian seem to be, or let's say other type of experiments seem to be, or linear Gaussian related experiments seem to be too simplistic. And then for this experiment I will talk about now, robot localization, we have, let's say, less control about, let's say, the location and also the relationship between the state and also observation. But also this is an interesting experiment that that's why we use this as a common data set for us to evaluate the algorithmic performance. So here, what we do here, so what is the setup? So there's a maze environment. So there's a maze like this, and robots can move according to the path there. So there's a map, so the robots know about that. And then what the robot looks at are those robot cameras. So it has a camera there, but it's a simulated environment developed by Google DeepMind. And then the states have the location and also orientation of the robot. So for example, XT, YT, those are just X and Y location. And this rho T, which is the orientation of the robot. And then the dynamic model looks like this. So basically ST plus 1 is equal to the state at the previous time step, xt plus the velocity times the cosine of the orientation and plus some other variation. And then the orientation also is updated in this way. And similar to the disk localization experiment, we can encode the observation into features to estimate the likelihood. And this is something actually we haven't had a good insight how to do this better. Because, well, for images, it's very high dimensional. You really don't want to directly estimate or approximate the likelihood using the observation. So we directly map it to observation into a feature, and then just assume that this observation was this conditional likelihood based on with the feature is approximately equal to the observation conditional likelihood. But this is actually one assumption that perhaps we can improve. And then we also use that feature, that encoding instead of observation to construct the proposal distribution. And then the loss function, similar to the, let's say, destruction example, can be RMSE loss and auto encoding loss. So here we haven't shown the, let's say, the elbow-based loss results, because this is just in the setup here, it will assume that we have those ground truths, but also there are some separate experiments. So just with those simpler, more controlled linear Gaussian example, we have evaluated some other results. This is more difficult than the disk localization task because they are uninformative observations. Also, we need to consider the orientation of the object. And then in terms of the training, so we have 900 trajectories for training, each have 100 time step and 100 particles, again, using training and testing. So here's the filtering outcome. So basically, initially we have those particles, so circle there, and true location is over here. So basically, that's where the true robot is. And then our particle estimate, as you see, is that if you uniformly sample those particles according to a uniform prior, so it's in the center. And then once we start to perform filtering, so we receive the observation, and we can see that the particle estimates start to move towards the target location. So showing that it's doing reasonable filtering, and also those particles kind of follow the true target location. Yes.
So here, the objective is the distance between the blue star and the green triangle, right?
Yes.
So the particles can be wherever, just that the mean has to be close to the true mean.
Yeah.
So we don't really converge around the actual point.
Well, this is just one type of training objective you can choose. And then if, let's say, another choice with a supervised learning is that you assume that there's Gaussian mixture, you maximize that likelihood, then it will also kind of force the particles to be also closer to the true, let's say, location, because otherwise, yeah, that one can give you higher likelihood. It's just one choice that we use, and it works well in engineering problem.
Another question, have you looked up what are the features that the filter is learning? Because, I mean, you know, it will be interesting to see, because usually in robot localization, you have some landmarks and you are tracking your position with respect to the landmarks.
Yeah, I don't recall that we have looked at this. Perhaps Xiong can jump in from the online to see whether some of the features have been looked at. And what we do here is that because that feature encoding outcome, whether we can decode the feature through the observation space and then see the difference between the, let's say, that reconstructed observation with the real observations, that has been part of the training loss. So there needs to be something done there. But whether some landmark have been, yeah, that is actually something interesting to look at. Yeah. Because right now, I think we're basically using the particle cloud to see whether the mean and also particle clouds follow the true trajectory. So that is what we are looking at.
The likelihood was unknown, but the transition model is known in this example.
The likelihood is what? So sorry, could you repeat? So likelihood, yes, is unknown for sure.
And the transition model is known.
Not known because we also learned it. Well, in this case, so we don't learn it. So there are different approach on this. So for example, for normalized flow differential particle filter, so we basically, I think it's a combination. I need to again check with Xiong about this. So it's a combination. So there are those physics-based models that when we have the information we can incorporate, we incorporate it. But in this case, because there's such a well-designed model, how that is used in the normalized flow-based differential particle filter. So Xiong, if you have heard about the question, maybe you can comment here.
I think I can answer this one.
Okay.
We've done a couple of things. We tried a couple of different models, giving the learning procedure a different amount, like different strength appliers. I believe standardly we do use that physical model, and with the case of robot localization, we have like control inputs to the robot, so we can have, for example, go forward X amount. We have that, but then we learn the noise distribution on that. But we still like say, assuming it's gone forward that amount, we can work out what it should be.
To me, I think the more sensible approach, just to make it more versatile, is directed to use a normalized flow-based approach. So assuming that you don't know about that, but again, for practical problem, it doesn't make sense for you to throw away the physics information if we can use it. And also in that, our initial work using conditional normalized flow to construct the dynamic model. So we basically have a prototype dynamic model. So using the additive Gaussian noise. So what we can do is to use, let's say, approximation. So assume that we have some information about the physics model. So we use that to construct such a simple, let's say, Gaussian model, but we don't assume that it's perfect. We can just stack a normalized flow layer there just to make it more flexible. So if there's any discrepancy, there's a mechanism to correct that. Yeah, very good question. And then if we evaluate the numerical experiment outcomes, so the validation RMSE decreases while we train, and we can see that this NFDPF again, so exactly the same setup gives a slightly lower validation RMSE compared to the other. I think it's really the important part to me is about this approach that we ensure that both dynamic model and the likelihood, they are real densities, so that we can basically ensure that there's no approximation there in terms of those essential components. And then we also show that with those things there, we can get the better filtering outcome. And then we also tested in different maze environments. So there are small mazes, larger mazes, and larger one. And we show that this NFDPF has given some interesting, well, smallest filtering results there. The summary of the differential particle filter. So in terms of dynamic model and proposals, they are closely related. So I put them together. So replace the sampling operation with parameterized deterministic function. And so through representation trick, made differentiable through well, the representation trick. And also we can use conditional normal flow or the, let's say, vanilla normal flow for those two components. And then for measurement models, so most measurement models are differentiable by say, but then the k-task is to really construct valid density. So normal flow can be used there, just in a slightly different way. Resampling, there are different ways to do that. So it's not exhaustive as we discussed. And then they have their own benefits and also shortcomings, and that can be really explored more. And then in terms of training objectives, so there are different training objectives. So when ground truths are available, there are mean square error. When ground truths are not available, we can basically maximize or log. Well, log likelihood of states is also assumed that the states ground truths are available, so you basically maximize that individually. But then when the states are not available, pseudo likelihood and also the elbow on the marginal likelihood estimator can be used. And future work will, I say all of those components, but also something that I really want to, I think it's really useful compared to, let's say, machine learning communities, that they have some common data set. And then everyone agreed on the evaluation metrics, and then those standard real world data set and metrics to really objectively evaluate all the algorithm with this, let's say, intersection between machine learning and also filtering to be really nice. So I talk about that Google data set, and that is something that we are right now looking at. I think it's just useful thing. The data set is massive, and there's different sensor measurements and also non-linear relationship. So how we can compare different approaches, not just between differential particle filter and normal particle filters, but also other sequential inference algorithms. That seems to be nice, but also other experiments could be useful, like more controlled experiments. Online learning, so I just discussed, those are more, let's say, offline learning-based approach, but also you want to have online learning. So if you think about deploying those filtering algorithms into your phone or into your autonomous cars, you really want to learn as you receive more data, adjust your dynamic model and also measurement model. And we have done some initial exploration, but I think we really expand, also evaluate those algorithms in more realistic setup. And then few shot learning, well, in terms of the data, so we don't always have, let's say, that big amount of, let's say, ground truth information. So how we can use limited ground truth information to learn an effective, potentially complex neural network parameter. That is something useful. And also in terms of smoothing and also other things, those are all interesting.